Okay, thanks, Steve. So thanks, Sifan. This is great. You already summarized the main theme of the talk, which is why do people use Stan? Charles just coached me beforehand. Charles Margosian, who's a postdoc here, just said you have to get across the message of why people use Stan. So I will try to do that during this. Sifan asked me to do something technical about how Stan works. I realized yesterday when I went to try to put the talk together that I had over 600 slides. So we're now like on year 13 of Stan, and I have developed a lot of slides, and I tried to collate them down to something manageable. We'll see how well I did, but I think this may go fast, but I don't really need to cover all of the material here. But feel free to interrupt if people have questions. I think Sifan's monitoring the questions and can let me know. So first of all, the big question, who is Stan? Stan is named after a person. It is not an acronym. Do not capitalize it unless you want to shout. It's named after Stanislaw Ulam, who was the co-inventor of the Monte Carlo method and, unfortunately, the co-inventor of the neutron bomb. And he's holding this really cool device, which is something Enrico Fermi developed to actually do Monte Carlo simulation for neutron diffusion. And Fermi actually had a physical device made that you can go look this thing up on the Wikipedia. It's super cool. Fermi was amazing. Stanislaw Ulam was cool, but Fermi was really amazing. So what is Stan? Stan is an imperative probabilistic programming language, and that means it's a programming language like C or C++ largely, as opposed to something like Bugs, which is declarative and lets you define a graphical model, or something like Church and all of its descendants, which are very functional, or something like PyMC, which gives you a hybrid of sort of declarative and functional and imperative depending on how you want to like interact with it. So a Stan program, and I'm going to give you some examples of Stan programs as we go. The main point is that it defines a probability model. And in particular, it declares data and constrained parameter variables. It defines a log posterior, which you can think of as a penalized likelihood if you're doing maximum likelihood. And then it defines posterior predictive quantities. And I will show you how all of that works as we go. Stan inference then takes a model that you wrote in data and it makes some kind of prediction, some kind of estimation. It does MCMC for full Bayesian inference using nuts. It does Laplace approximation and variational Bayes. Variational, we have ADVI and Pathfinder. And it can also be used for MLEs and to bootstrap for confidence intervals, although I think there's roughly 0 people who use Stan for that. It's totally set up. Our manual tells you how to do it. Why do you want to choose Stan? Well, largely because it's expressive, right? It's a particularly easy way to write your models down, and it's a domain-specific language. So it means the language is set up to match the way probability models are defined. And it's fairly robust. It usually works, and when it doesn't work, it signals where it breaks. This is still a tricky problem. I'm not claiming we have the diagnosis of bad fits problem solved here. It's relatively efficient. The time remains state-of-the-art on the CPU. We built Stan before PyTorch, before TensorFlow and JAX, before any like mainstream autodiff packages. We thought as soon as TensorFlow showed up that we were going to be dead in the water, but in fact, they have spent all their time optimizing for GPU, so Stan is still pretty state-of-the-art on CPU coding. And I would say the modal person who uses Stan has a 5-year-old Windows notebook with very little memory, like a few gigs of memory on it, right? We do provide multi-core and GPU support, but we're not competitive with things like TensorFlow for that. There's ongoing open source development. We're still actively developing features, expanding the math library, and the not so secret sauce, and I have a whole talk on this online on how Stan got developed and what made it popular. Really, I think the biggest blame for Stan being popular is the really great community that's been built up around it. There's so many examples, books, things like that written. And the documentation is very thorough. I've written most of our documentation at the high level because I really like to write doc. So let's go back to when we were first starting this project. So Andrew Gelman had hired me and Matt Hoffman. It turns out Stan was developed under the exact same grant that developed Julia. So the very first version of Julia and the very first version of Stan were developed under the same DOE grant, although we weren't working closely with the Julia team. And they were really kind of mad at us for not implementing Stan and Julia, but anyway, there's a reason we didn't do that. So anyway, what Andrew wanted to do was find a way to robustly fit and describe the models in his and Jennifer Hill's multi-level regression book. It went beyond what you could do with LME4 and something like that. And there wasn't like an easy way to write those models down. Turns out we never succeeded at writing a better regression language than LME4. We wound up building STAN instead. So I'm going to go over a bunch of problems and sort of what STAN did to solve them. So the main problem we ran into, initially Matt and I pulled the lid off JAGs and made JAGs. We could make JAGs at least 10 times faster if we put a few months of engineering effort into it, because it's very badly engineered. It's an amazing accomplishment that Martin Plummer built this thing on top of R's code, but it's not, you know, state-of-the-art engineering. But it turns out that just Gibbs and Metropolis are too slow. They wind up being diffusive samplers, and instead we need something like Hamiltonian Monte Carlo in order to be able to follow the Hamiltonian flow. That's the usual kind of topic for this seminar. Interpreters tend to be very slow and unscalable. So my own background was in natural language processing and programming language theory, and I'd spent about 10 years in industry before moving to work with Andrew. I used to be a professor working on NLP and programming languages. So what we decided to do was build a compiler, something that would compile or transpile to C++. But then we need gradients for the log posterior. And what we used for that is reverse mode automatic differentiation. We figured out how to do that because I wrote a post on Andrew's blog saying, hey, we need to use HMC. We need to take gradients. What in the world should we be doing? And I still remember when we were in Andrew's office looking on Wikipedia for what automatic differentiation was, because in 2010, almost nobody had heard of it. And we were like, oh, it's not finite differences. But the existing autodiff that existed at that time was really slow and limited. This was before PyTorch and TensorFlow, so we wound up having to engineer our own autodiff. Luckily, Matt had spent a lot of time in industry, and Daniel Lee, the other person who built the first version of STAN with me, also spent time in industry. So we had good engineering talent going into this. Autodiff requires functions that are templated on all their arguments in C++, so we wound up having to build our own C++ density and special functions library that we built on top of Eigen and Boost, two really core, really well-engineered C++. I would say maintaining this library and the I/O interfaces has been the main cost of maintaining STAN and developing STAN over time, right? Next problem we ran into is we need unconstrained parameters for HMC. You can do HMC by bouncing off walls and things, but if you're going to try to define like a positive definite matrix type, you want to be able to transform that into unconstrained parameters. So what STAN does is it automatically applies unconstraining transforms behind the scenes, then inverse transforms those back to the natural scale and applies all that change of variables. So STAN will let you declare a variable to be a positive definite matrix. It will handle all the constraining and unconstraining. Right now, there's a lot of interesting research, I would say, to be done on what the best forms of those change of variables are, because they affect the conditioning of the end result, right? You could think of it as sort of defining your own kind of preconditioner. And we found that some of the things we were using before for like the simplex transform are not ideal, and we're going to change those out real soon. We need something like the ease of use of bugs. I don't know if people still remember bugs. I guess it's still being widely taught, but I wouldn't have ever learned stats without bugs. So what we want to do is compile a domain-specific language, right? Something that would let statisticians, without having to think about all the horrors of C++, actually use all of our fast underlying implementations. So when we were thinking about this, we decided that the pure graphical language that you had in something like bugs was really inflexible. So instead, we went with an imperative language, which really means that in STAN, you're really writing a differentiable function for the log density, rather than defining the nodes in a graphical model, for example, right? HMC, there were many reasons HMC wasn't used. The main one was that you couldn't calculate derivatives, but it is also nearly impossible to tune for the step size and mass matrix. So this was the problem that Matt solved while we were working together, which was he developed NUTS, the no U-turn sampler, which figured out the path length. And then we estimate a mass matrix and step size during warm-up. I would say my main research that I'm working on right now with Nawaf Bourabi and a bunch of other people is related to this, related to doing better adaptation. We've got a lot of really exciting stuff that hopefully somebody working on this project will tell this group about soon. We need efficient up to a proportion density calculations. Like all this MCMC, we don't need to calculate normalizing constants. We did that through some really clever template metaprogramming in C++ that Daniel Lee came up with. It was really nice. Most of the systems that existed before us had very limited error checking, like bugs just seg faults and throws up a core dump if something goes wrong. It couldn't be much worse than that. We have very static typing, very informative error messages and exceptions. A lot of the early systems had very poor numerical stability, so we worked very hard getting the algorithm stable. We had to deal with this because the library implementation of log1p is stable, but we had to implement derivatives. So we had to make all of those stable as well. So we had to apply the same tricks the library functions use to make all this stuff stable, right? The big problem is we started this with a couple people, and none of us actually who started this project were really expert in Bayesian statistics at this point. We were all much better at engineering and computer science. All three of us, me, Daniel, and Matt, came out of computer science. So we wound up expanding the project team with people who were much better at statistics, like Ben Goodrich, and other people who are much better at software, like our current software engineers, like Steve Bronder and Brian Ward, who work with me here at Flatiron. So we also then ran into the problem that, oh my God, we've now got an expanding code and project team, right? We went from being 3 people sitting in an office together to like a dozen developers. So we had to impose a lot of process through GitHub where we branch, pull request, code review. One piece of advice I have, if you're doing code, get it code reviewed. It is the single best thing you can do. Have another person just review the whole thing, make sure it's understandable, make sure you haven't missed obvious optimizations. We went with Jenkins continuous integration, and we're still to this day refactoring and simplifying code. We have a very heterogeneous user base in statistics. So one of the reasons we built Stan the way we did is so that it could interface into R, Python, Julia. We have a lot of domain-specific tutorials that help people get started, and we have a lot of non-statistician and non-programmer users. I was surprised at how little applied statisticians were able to actually program in an imperative language like this. So it's turned out to be much more popular than Stan itself is all of these interfaces that live on top of Stan and use Stan as a low-level compute layer. For instance, hundreds of companies are using Prophet for time series forecasting. Facebook built it to model demand of services like messaging throughout the year. And it's just a simple linear additive model, but it's very well encapsulated by Facebook, and it runs in R and Python on top of Stan. So it's very, very widely used. It's probably as widely used as Stan itself is used, for example. I was also very, yeah.
Oh, sorry, I thought you were finished on this slide. There is a question about the definition of reverse mode. Is as in reverse mode autodiff.
Oh, I'm going to get to that later in the talk. I'll show you how that works, actually. So it means basically that you build up an expression graph when you evaluate, and then you take a reverse pass over the expression graph, passing partial derivatives. But I have some examples and some graphs that show that later. Also, I didn't like all the restrictive licensing of all the other packages, so we just made everything open source. We made it BSD licensed and Creative Commons license for the doc to make it as reusable as possible. This is really critical if you want companies to use and contribute to this, not having things be GPL. Anyway, what does Stan do? Let's get into some more technical stuff and some examples. The main purpose of Stan is to estimate expectations with respect to some probability model. So I'm assuming somebody's given you a posterior density, P of theta given Y, however that happens. Usually you write that down in Stan in ways that I'll show you. The main go-to procedure in Stan, no matter what kind of inference we're doing, is sampling. That's mainly because we work on the unconstrained scale. So even if we're doing something like Laplace approximation, we want to return answers, we sample from the Laplace approximation and then transform back to the constrained scale. So what are the main things that we do? They're all expectations. We calculate posterior parameter estimates as the expected value of the parameter theta given the data y, and that's just a simple MCMC. They're all simple MCMC calculations that look exactly the same. Variance is just the expectation of the difference from the expectation squared. right? Posterior event probabilities, if I have some subset of the parameter space A, and I have an indicator function that is true is 1 if something's in that set, then the probability of an event, right? Oh, sorry, that should just be written, the probability of A given Y is the expectation of the indicator function, right? Posterior predictions for new data look exactly the same. It's just the expectation of the predictive density given theta conditioned on Y, right? We can do posterior quantiles in the ordinary way by just taking empirical quantiles on the actual draws. That's the only thing that's not an expectation, but if you turn it around, you can think of it as an expectation as well. So let's go through a first example. And I like this first example because it was the very first example of Bayesian statistics, right? That was actually carried out as far as I know. So Laplace took data from live births in Paris where there were about 10,000 more boys born than girls. And he had the question, what's the birth rate of boys versus girls? And the question 2, is a boy more likely to be born than a girl? Right? Bayes in 1763 set up the notion of a Bayesian model, but it wasn't until Laplace came along and could actually work with Euler's beta function, standardize everything, actually compute the posterior for this analytically. We don't have to be as smart as Laplace, who, by the way, did this with like pen and ink and candlelight. We've got a computer, so we can just do this very easily, right? So here's what Laplace's model looks like in Stan, right? So we're just going to define some data. This doesn't even read data in from the outside. I have just hard-coded this data in a transformed data block. What's the number of males and the number of females? We declare a single parameter, theta, that is lower bounded at 0 and upper bounded with 1. That's because it's going to be a probability, right? And then our model is just going to be a binomial draw of male plus female given theta, right? So it's just a simple binomial of male births given the rate of male births of theta, right? By default, theta gets a uniform prior. In Stan, every parameter by default gets a uniform prior on its declared support. So this is going to be uniform from 0 to 1 as a prior, which is why we don't need to write it down here. You could also add a beta 2 prior, like I think Laplace did, or Laplace suggested later. Generated quantities is something that happens after the model definition. The sampling part of Stan just takes the parameters and model and defines what exactly you're doing. The generated quantities block is something for doing posterior predictive inference. It's something that only happens once per iteration, as opposed to the model and parameters, which need to get evaluated during the Hamiltonian Monte Carlo algorithm. So once we're done, we can take this generated quantities, and this is going to just define an integer that takes on a value of 0 or 1 based on whether theta is greater than a half, right? So this is our indicator function for the event of more boys born than girls, right? So remember, we need an indicator function. Then we're just going to be able to take the posterior average of that indicator function and get an estimate of our event probability. Right, so we just fit, this is an R implementation. I did a silly number of iterations because it's really fast when you have a model this slow. And I'm going to fit the 99% posterior probability intervals. That's the other reason to take a lot of draws, is if you want to take narrow quantiles at the end, then you narrow intervals and, you know, low or very high quantiles here, then you're going to have to take a lot of draws to resolve those. So what you can see is theta has a mean of 51% with a with a posterior interval, 99% interval of 0.508 to 0.5112. Theta greater than a half is 100%, right? So Q1, to answer Laplace's first question probabilistically, right? Theta is 99% certain to lie in that interval, given this model, right? Question 2, Laplace claimed he was morally certain that boys were more prevalent. Stan reports 100% here for this probability. It's not technically 100%. I think Laplace calculated it to 1 minus 10 to the minus 42, right? So it was nearly 100%, right? We can't even represent that number, 1 minus 10 to the minus 42, in double precision floating point. That number, if you try to carry out that arithmetic, will just give you 1. Unless you go up to like quad precision arithmetic. So anyway, very simple example of what Stan does. Let's look at something a little more complicated. This is a linear regression, and it does prediction for new data, right? So we have a number of dimensions, k, that we're taking for the regression. And then our data is going to be a matrix, just a design matrix of x with n observations. Y is going to be our actual observations. N is our number of observations. Then we're going to have this n tilde and x tilde, which are held out data for which we want to make predictions. So the idea is we want to predict y tilde based on x and y, right? We want to do posterior predictive inference for an unknown y tilde, given everything we've observed, right? So we lay out the parameters. Here it's a vector of parameters for the regression coefficients and a lower bounded at 0 sigma for the scale. We have a normal distribution that just says y is normal, centered at x beta with sigma error. We throw a couple priors on, assuming everything's unit scale. If it wasn't, you'd want different priors here, though you'd probably be better off standardizing your data. In practice, in our modules, if we have something like this, we do a QR decomposition of X and work with the Q matrix to make sure we get orthogonal components. And then we put everything back together for the user at the end. Right? It's one of the nice things you can do if you have an encapsulated package. That's a pain. You can write that in R and write that in Stan, and our user's guide shows you how to do that. But it's much easier to go up to one of our R interfaces and just throw it all in straight. Right? And anyway, the predicted value here, now we're using generated quantities a little differently. We're applying a random number generator, right? And we're centering this random number generator around x tilde times beta. Beta is going to be over the posterior, and the noise sigma is going to be averaged over the posterior. So this gives us posterior predictive inference. It gives us posterior draws for y tilde. So the uncertainty in estimation comes into the Monte Carlo that's going to give us different values of beta and sigma over time. This random number generation gives us the intrinsic sampling error in the model, right? We can never reduce the uncertainty in y tilde below sigma, right? Because that's just what this model is. So we compose the two kinds of uncertainty in our posterior, the estimation uncertainty and the sampling uncertainty, to get our posterior predictive uncertainty. Right, so this is, I would say, a very standard use case for Stan or for Bayesian statistics, which is to do something predictively, right? It's like I've measured something in the past, I want to predict it in the future. I've measured it for some subset of the population, I want to measure it I want to estimate it for the rest of the population, right? So let's consider a couple more complicated models in Stan, which get closer to the kind of scientific applications that I find particularly interesting. So this is like the hello world example for solving ordinary differential equations. And we're just going to show how it goes down in Stan. Right? Lynxes, the thing on the left, are predators, and they prey almost exclusively on snowshoe hares, and they are almost exclusively the only predator of these hares. So this makes some very nice data. We have data going back to the 1800s from the Hudson Bay Company through the early 1900s, which measures the number of pelts that were actually captured of different kinds. So there's wolverine, lynx, and rabbit. So the top two are rabbit and lynx pelts. Right? So somebody just transcribed that into a database, and then we can plot it. Right? So we can plot the number of pelts that were actually captured by year. And you can see it has strong up and down where there's a bit of a lag on the lynx going up and down. A standard way to plot this in this world is a plot over time where you start with the original values and you show the lynx versus the hare on the X and Y axis. What we're assuming in doing this kind of model, that the number of pelts we capture is proportional to the population. Right? We don't really measure the population in a direct way. We're just counting the number of pelts that the trappers come back with. So you have to be careful about these kinds of assumptions and what kind of claims you're making, because all kinds of things can get in and confound the answer. So 1927, Volterra, you can see Vito Volterra, as you can see in the upper right, wrote a paper with a model for this based on differential equations that had coefficients, and that was his theoretical time series. And you can see his theoretical time series compared to the empirical one from the Hudson Bay data below, right? And it's just a simple differential equation model that has coefficients for the growth of the prey, the shrinkage of the prey due to predation, the predator shrinkage due to not having enough food, and predator growth from predation, right? So it's just a very simple system of two differential equations. The dynamics of these differential equations lead to exactly the kind of oscillations that we observed. So let's see if we can use this model to fit the data. So what do we do in STAN? Well, we have this differential equation here that Volterra gave us. So we just write that down as a function in STAN. We've got two variables, u and v, and we're just going to write the system derivative function. There, we're packing up all of our variables into an array theta. We can actually do this a little more elegantly now with polyadic functions, so you wouldn't need to pack all this stuff up. And then what we have in the rest of the STAN model is that we have UV hat. So we're going to have this dynamic system, and we're going to take an initial starting point, which is going to be unknown, and we're going to take it z naught, and we're going to take an initial time t naught, and we're going to say, hey, we want solutions at all of these particular times. And then we're going to assume that our data, which comes in the form of the links and hair pelts in the columns of this matrix here, are going to have log normal distribution. So it's basically going to be, there's an error term for the prey, an error term for the predator, making this log normal, make sure we don't run into, weird artifacts like predicting negative amounts of prey or predator. You'd be surprised. I was working with like NOAA on a model, and their standard model for fishery stock allows negative solutions, and they just fudge the hell out of this thing. I think it could be done better, but they were very set on their own model. So anyway, you just code it up. This is basically how you'd write the model down in math, and you basically just code it up like this in STAN. And here's a plot of what the fit is. On the left, in red, you actually see the measurements. Those are the actual measurements of the hair and link population. The green gives you the predictions, or the turquoise gives you the predictions. And we've done posterior predictive inference just like we did for the linear regression going into the future. Right? Because we have this log normal error model and we have the way it predicts, we can just keep predicting into the future where, obviously you don't want to extrapolate too far. It's statistics. We're not expecting this to go, global warming is going to affect this and so forth. But the model's a reasonably good fit. That's why this is the hello world example for solving differential equations. It actually fits really well. Here's what 100 posterior predictive draws look like. I just take 100 draws of those parameters and see what the orbits would look like in terms of the pelts. Again, links versus hair over time, right? And here's what the parameter estimates look like. There's nothing really much to see here. You can see that the effective sample size is really good. The R hat values are all near 1, which means it's converged. The standard error is close to 0 because we've got a lot of data and we ran it long enough. So basically business as usual here and looking at the answer for this. I do want to summarize, though, what this looks like. What did we do? We started with a mechanistic forward model, right? Some scientist said, I think this is how this process looks. It turns out I'm working on a project with our biology group right now, which started exactly the same way. It's a model of fly jumping and habituation, and it started out with a differential. They're like, here's our differential dynamics model. Can you fit this? Right. So I'm actually doing this for a real problem right now. So we start with this, you get a friendly scientist involved, learn enough about their world to code a model. There's an error model that says we make observations. We're measuring these pelts. We don't expect that to perfectly reflect even, the number of animals. So we're going to have some error there. We added some weakly informative priors to fix the scale, right? We use STAN to do sampling from the posterior, and then we just do plug-in estimates of everything. Right? So just standard Bayesian inference here. Let me give you a second example. Right? This was something that Brian Warden, who's a core STAN developer who works here, and I did to reproduce one of our postdocs papers about holographic coherent diffraction imaging, or as I like to say, Star Trek mumbo jumbo, because I have to say this is the most Star Trek kind of thing I've ever worked on. Just saying this sounds cool. We did it, though, just to illustrate our complex numbers. We added complex numbers to STAN a few years ago and added fast Fourier transforms and derivatives of that. And we just wanted to provide an example for our manual for like how people can use the FFTs and numbers. So here's the problem. You start with some biomolecule. This is some giant thing called a Mimi virus, and a reference sheet. So this is a real biomolecule sitting there. It's tiny. And then you have this reference sheet, which is like that, or it's usually simpler. This is the ideal reference. And then what you do is you shoot X-rays through the reference and through the biomolecule at a certain spacing, right? Then we're really careful to stop the beam because the beam's going to burn everything out in the middle if we don't occlude it a little bit. And then what we're going to do once we do that, so we fix our biomolecule, we fix this reference array, we shoot X-rays through it. They are going to diffract off of that thing and provide this pattern. This is a plot of the raw data that we observe, except in the middle, we've basically occluded that with a little thing called a beam stop. Otherwise, we would get so much energy concentrating at the middle through the diffraction that it would just burn everything up and burn the sensors up. So we block that. And when I say we, I mean whoever's doing this in the lab. I have no idea. I could show you pictures of what it looks like, but I've never done this, right? And then you observe the photon counts on a sensor. So what we've done is we've set up a grid, just like a camera, right? That's like 512 pixels by 1600 and some pixels. And we've literally counted the number of photons that hit each frame. And it turns out this follows a process according to whatever the relevant particle physics theory is, right? We know that this pattern of diffraction is going to form a Poisson process. And the expectation is going to be given by the fast Fourier transform, or the discrete Fourier transform, of the image that we're actually getting. We have the reference array there so that we actually identify this model. Without some kind of reference array, the model's not identifiable, right? So how do we code this in Stan? Well, we code up all the data, the image dims, the registration image. We need to pad that a little bit in between. We need a size of a beam stop. We have the average photons hitting each pixel and then the observed number of photons. The average is just going to help us normalize, and we could have computed that in the model itself, right? Then we're going to do some transform data. That is, we're going to create the beam stop image. Then we're going to set up parameters. The parameters in this case is the actual image, the actual pixels in the image, which we assume are black and white and have an intensity between 0 full black and 1 full white. And then our model just says we start with our image, right? Our actual pixels in the data. We apply the padding to it of a given size with our beam stop, and we get what we expect. This whole thing is sent through a two-dimensional fast Fourier transform and squared. So the thing is, we don't actually observe the complex result of the fast Fourier transform. That's a complex number. We only observe its magnitude squared, right? So this causes what's called a phase retrieval problem, where we're trying to actually figure out the magnitude and the phase of the complex numbers. That is the real and imaginary components of them, right? We figure out what the expected number is, lambda here, and as we said, the likelihood is just a straight up Poisson observation. Our prior is just going to be uniform, right? So we just literally code this process up in Stan pretty much as written in the math. This took us like 2 hours to get this working. Then we turn Stan's crank to solve the inverse problem. We do this using OBFGS. We also fit it with nuts and ADVI. We have a paper where we go over all this. For the 256 by 256 pixel thing, Stan takes a couple minutes to do this with inverse, by doing optimization. It takes a couple hours to get a reasonable solution with MCMC. But as far as I know, nobody's ever solved this problem with MCMC before. It produces some interesting results in terms of the likelihood. We consider different priors, but you can see here what happens. The image on the left is what we can recover if we on average observe 1 photon per pixel. The right is what we can reconstruct if we can observe 10 photons per pixel. Turns out we cannot do the thing on the right. Once we've done the thing on the left and shot 1 photon per pixel with X-rays at this biomolecule, we've essentially destroyed and denatured the molecule. So we can only get the thing on the left in reality, because if we shoot too many beams at a molecule, it destroys it, right? And we can do either the MLE or the Bayesian estimate of this. Right. Okay, so that's a couple examples of how to use Stan for scientific problems. Let me jump up a little higher level about Stan. Where does it work? It works pretty much everywhere. We have interfaces in R and Python and MATLAB and Julia, so forth. It's all standards compliant, open source. We have high-level interfaces like RStanArm and BRMS, statistical rethinking, Profit. These all get used more than Stan itself. And when I say more than Stan itself, I'd say by like an order of magnitude more, right? I'd say 2 out of 3 of our messages on our mailing list are BRMS, right? And we get on the order of like 15 new queries a day on the mailing list. Who's using Stan? Best of our estimates, 100,000 or more people have used Stan. Not really clear what a user is. Is it just somebody who uses it in class? Because there's like dozens of classes that just use Stan to teach Bayes, right? But I think the thing that's a better measure is we have about 7,500 people at this point registered for our users group. There are millions of downloads. Downloads don't mean anything, but we have over 10,000 Google Scholar citations for Stan now. So people are really using it to solve all kinds of problems. But people ask me what Stan's used for, and pretty much anything in statistics it gets used for. I like that all the competitive baseball teams all use it, for instance, and they hang out on they try to recruit our users. They don't pay very much. They recruit baseball nuts, right? So they try to get people who really know Bayesian stats, who love baseball and want to come work for it. So if anybody you know wants to work for a baseball team, they're pretty easy to get jobs there if you're good at stats. Documentation. This is really critical. Over time, we've broken our single document into a user's guide, a reference manual, and functions reference. I was very adamant in our user's guide that we keep the level of statistics fairly low and the level of math fairly low and keep the level of completeness of examples very high, right? So a lot of it's very pedagogical, just introduction to models, introduction to Bayesian stats. Also, a lot of examples in people's domain. People come to software like this and they're like, hey, I work on population ecology. Has anybody ever built a population ecology model? And they're like, yes, because there's literally thousands and thousands of models out there written in Stan, right? We have very good installation and getting started documentation by interface, and we're very responsive on our mailing lists. There's dozens of written and video tutorials, including at least half a dozen full-year courses in Bayesian statistics using Stan. There's all kinds of model sets from different books translated to Stan. I think this list is like 5 years out of date. Books using Stan. I actually went down a rabbit hole yesterday of looking up books using Stan, which we hadn't updated this list in a while. There are quite a few. Interestingly, the second Mark Carey, when we did a tutorial about 10 years ago in Switzerland, said there's no way ecologists are ever going to use something as complicated as Stan. And now he has his name on a Stan book. So there are a lot. Yeah, no need to read this, but there's like 20 plus books written that either have a chapter on Stan or entirely written in Stan. So getting into a little more detail on what Stan is, right? Stan's really a programming language. It's not a graphical specification language, right? It's Turing complete, in fact, meaning that you can write any program you could write in C, you can write in Stan, right? And its main purpose is to define differentiable log densities and predictive quantities inside of generated quantities, right? So unlike things like bugs, it allows reassignable local variables and scoping, full conditionals and loops. You can write your own functions, including recursive functions in Stan. So it really does let you very flexibly write models down as long as you can specify the density and ideally keep that density continuously differentiable or not too jumpy. Then Stan layers black box inference on top. But what it means is because Stan's a programming language, there's different ways of writing a Stan program have very different implications for efficiency, for memory locality, all of the good stuff you'd have to think about when really programming. Now, in our interfaces like BRMS, we just do a good job of that for everybody. So the basic blocks in Stan, we have a data block. And everything in Stan, every variable, if you've noticed, declares its data type, its size, and any constraints on it. The data just gets executed once, gets read in once, and then the parameters get read in every log density evaluation. So if you're doing nuts, that may involve 100 log density evaluations per transition, or sometimes even more. That involves transforming unconstrained parameters to the constrained scale and doing the Jacobian adjustments under the hood for that. So that the user can just write probability statements in terms of the constrained variables. And then the model just contains a bunch of statements that define the posterior log density. There's a running accumulator of the thing that's going to be returned to the log density, and all Stan statements do is add to that. Right? Then we have some derived blocks. So you can take the data and transform it. That just happens once. Transform parameters can apply to parameters. That happens every log probability evaluation, and you can monkey with the Jacobian there if you want. And generated quantities happens once per draw, but this is very efficient. It executes with a double type rather than an autodiff type. So generated quantities executing the same code is at least 4 or 5 times faster than the rest of Stan. Plus, it only does it once instead of once per iteration. So usually the things in generated quantities are about 50 to 1,000 times faster than the rest of Stan. So you can really go crazy in the predictive block here without much performance hit. The model reads and transforms the data. It does this once for optimization and sampling per chain, right? And generates the transformed data. The log density, I've already said this a bit, but it basically builds an expression graph, which I'll say a bit more about later. And then it accounts for the change of variables. So for instance, if we have a positive constrained variable like x, if we have a positive constrained variable like x, what we do is we log transform it to y, and going backwards, we apply the x transform. So we have to add the log of this determinant in every time we have a positive constrained variable y, right? And then we can actually work with y, right? The log density gradient, I think I'm going to pass on this from now and come back to do this. The point to keep in mind is at the bottom. Using automatic differentiation, if you have it well implemented, the time to evaluate log densities is usually a factor of 3 to 5 times the cost to evaluate the gradient cost is about 3 to 5 times the cost of the log density. And then once you're doing gradients, the log density is free. So log density plus gradients takes about 5 times as long as just a log density using autodiff. It takes a lot of memory, though. It takes on the order of 40 bytes per operation involved, right? So you can often run into memory issues that can slow things down as well. And then generated quantities, as I said, is used for event probability estimation, predictive posterior, and it's very fast compared to everything else. These are the different transformed parameters that we have. We have lower and upper bounds. We have simplexes, we have ordered bit rates, we have unit length parameters, we have covariance and correlation matrices, we have Cholesky factors of these as well, and we also have some to zero constraints, which we just added in the most recent release. Oh, and we added left and right stochastic matrices in the recent release too. And then I've already said this. Right, here's the variable and expression types. This is basically just writing in code what I told you before. We have integer, real, and complex types, and then the various matrices and vector types. The reason we have this is that now if you have types and you know you have a row vector and you know you have a column vector, you can multiply them together and get a scalar instead of taking two-dimensional matrices, multiplying them together, and now you get a 1-by-1 matrix. Now, I know a lot of the systems try to overload this, but Stan just took the clean approach of defining simple types, right? It also distinguishes integers versus reals, which can get people into trouble, just like a regular programming language does. There's a lot to say about that, but probably not during this talk. We allow arrays of any particular types. The thing that we have not added that we really need to add is sparse arrays and vectors and matrices and ragged arrays. Sparse things are very complicated because of the linear algebra, but ragged we should be able to do, right? And this isn't worth saying, but I'll just flip over these. That we have the basic logical operators, basic arithmetic and matrix operators, assignment operators that work with all the kind of overloads you would expect, and a ton of built-in math functions, everything to like Meyer G functions and Bessel functions and incomplete gamma functions, all the crazy stuff you need to compute derivatives of things like CDFs and inverse CDFs. A lot of built-in matrix functions, basically all that you would expect. Does all the usual broadcasting, does eigenvalue, QR decomposition. We have FFTs now, does all the reductions in terms of norms and sums. And it has a lot of specialized code for triangular and positive definite matrices, because a lot of cases you know you're dealing with triangular things and you can really speed up the operations. Atomic statements. The thing that's probably most confusing about Stan is the statements here, y, normal, mu, sigma. Really, all they do is exactly the same thing as the next line. All they do is increment the log probability that's going on, right? So you keep this log density that you're calculating. When you say y is normal mu sigma, you just add the log of normal y given mu sigma to the log density. Right? And we have typical assignment statements. You can make blocks to introduce local scopes. We have all the usual for, while, conditional, break, continue stuff. We have side effects that do print or reject. As I said, sampling just increments the log prob. So here's the explicit example. Those two statements are identical in terms of what they'll actually do, at least up to a constant. And then we have local variable scope blocks, which are not very interesting. Users can define their own functions, all right? And then use those functions in their model. Some users build like 10-page long Stan programs, and they bring in a library of user-defined functions. They have like 50 user-defined functions. They often then send these things to the mailing list, and we're like, good luck. We don't know how to help you debug a 10-page Stan program. Right, we have special user-defined functions to increment PDFs for RNG, so everything can work well with the language. You can define your own PDFs and CDFs and use sampling notation with them. The target increment function, yeah, that's very technical. The random number generation, we can only use that in transformed data and in generated quantities. It doesn't really make sense to do random number generation in the model block. At least if we did, we'd have to do a bunch of reparameterization gradient tricks, right? We have a differential equation solver, which I've already given you examples of. We have stiff, non-stiff versions, and one thing that I think is kind of in between. We calculate the derivatives. Originally, we did this by coupling so we could get error control on the derivatives, but we've moved to using much more efficient adjoint methods. One of the reasons we wrote autodiff the way we did initially was much more like the way PyTorch eventually decided to implement autodiff. It allowed us to take something like an ODE solver way back in like 2011 and just autodiff right through the algorithm. That is not a very efficient way to do this. What we really want to do is apply the implicit function theorem, apply a proper adjoint method that's going to control memory and give us more accuracy, which is over time, our ODE solvers have matured into the right way to do this. When we first started, I didn't even know the right way to do this. So, we also have other built-in solvers. All the gradients for these come through the implicit function theorem, which you can read more about. Charles Margosian wrote a tutorial on how to do all of these. There's the differential algebraic equation solver. There's a one-dimensional integrator, which you can use for CDFs. There's a root finder that people have used for inverse CDFs. There's hidden Markov models that use the forward-backward algorithm built in. Right? We have a big library of distributions, including some of our own, including reparameterized ones like a binomial on the logit scale, things where we can compress the autodiff and make the linear algebra and other algebra more robust. We will build compound distributions. Print and reject. One thing that's very important is we vectorize statements like this. So if mu or y are vectors here, this is going to be much more efficient, not because loops are slow in Stan. It's not like Python and R because everything's compiled down to C++, so the loops are really fast. It's that autodiff is much more efficient. If sigma is a scalar and mu is a vector in this operation, you only want to compute log sigma once. Log sigma is really expensive, right, compared to anything else for the log density here. So you do that once and reuse it. Our functions for the log densities are smart enough to do that under the hood. Like to say, oh, sigma is a scalar, mu and or y are vectors. I'm going to compute log sigma once. So that's why our vectorized log densities are more efficient, not because loops are slow. Parsing compilation. Oh no, we don't do this anymore. This is an out-of-date slide. We've moved to OCaml, right? I don't need to tell, so there's a language called OCaml. We do all of our translation. And I don't need to tell you guys, we do Hamiltonian Monte Carlo. The way we do adaptation, right? We're just doing standard versions of nuts. We do 3 intervals of adaptation in Stan. We do an initial fast interval just to find the bulk of the probability mass, and we use a unit mass matrix for 75 iterations. This is almost always sufficient to actually get to the bulk of the probability. Adrian Seabolt has a really cool implementation called NutPy in PyMC that initializes with the absolute value of the gradient, which turns out to be the geometric mean of a unit gradient and the outer product of gradient approximation, which the expectation of that's the Fisher information. So things like LBFGS use outer products of gradients to estimate Hessians, really estimate inverse Hessians. I'll get back to you on which way around it is. So we're probably going to be moving to do, we just did a bunch of evaluations and it looks like NutPy's version of this is much better than ours. So we're probably going to be changing Stan very soon to do this. Phase 2, what we do is we start with a window of 25 iterations. And at the end of that window, we estimate a mass matrix just based on the draws. Then we double that window to 50 and do it again. Right, so we gradually leapfrog up the estimation of the mass matrix and the actual sampling in the second phase. There's also a cool innovation of this in NutPy that actually uses the geometric mean of 2 things: the empirical estimate of the covariance from the draws and the empirical estimate of precision that you get from the covariance of the scores being the gradients of the log density. So the posterior, and this is for a normal distribution. So if you take a multivariate normal, the posterior for the covariance of the score function is the precision matrix. So he uses these to blend these together. And then there's a final fast interval that just does a fine tuning on step size that I think is 50. I think that's actually 100 iterations now. So other than that, we're just doing HMC the way it's sort of written in Michael Betancourt's paper and the way we've written it up more recently. We do Laplace approximation exactly the way you would expect. We work on the unconstrained scale, we optimize, we compute the inverse negative Hessian for the covariance, and we take multivariate draws from that. And then we transform them back to the constrained scale. Right, this doesn't really scale very well in dimensionality because it involves this quadratic term for the Hessian, but you can do it. And then we do black box variational inference. I'm going to skip over this in the interest of time and hop up because I think or should I stop here, Sifan, since there's only 5 minutes left? I think we should maybe stop for questions. In which case I will not get to the auto diff, but let me just put that up here. So let me just say, let me say one more thing and stop, which is I promised to answer the question about autodiff, how this worked. So this is how automatic differentiation works. So this is computing the log of a normal density of y given mu and sigma just for scalars. So what you do is I wrote out over here the log density for that. Right? And this graph just builds that up. Here's y minus mu that comes from over here. Here's y minus mu over sigma. That's it raised to the power of 2. That's multiplying it by minus a half. That's subtracting the log of sigma, and this is subtracting this constant. Right? So you build this thing up, and it's called an expression graph, and it's a graph because you can get reentrancy if variables are reused. Then what we do to calculate derivatives is we start at the very root of this graph and assign a 1. And that values that are going to be in each of these nodes are the derivative of the root with respect to that node. So we know that that initializes up here at 1 because the derivative of something with respect to itself is 1. Then all we do is we go down this graph and we take the gradient of the input with respect to the output and we multiply by the adjoint value and add it downwards, right? So all that happens is each of these arcs is going to have the partial derivative of that operation with respect to its input. And then you're just going to multiply the adjoints and propagate them down. That actually looks like this, the way it gets built up. That's the order in which the expressions get built up. Here's all the partials that get built up along with them. So that's just detailing the way this gets built up, but we do it in a stack like this linearly. And then the auto diff just goes backwards through this stack, adding the adjoints times the gradients, right, to eventually get the right value. And you can verify that when we're done, the gradients down here at V1, V2, and V3 are what exactly you would expect here. Right. So that's how the auto diff works. It's expensive because it has to build up this whole graph in memory. Each of these nodes takes about 40 bytes of memory. So about the equivalent of, sorry, about, yeah, 8, 16, 32. Yeah, 32 or 40 bytes. Sorry. Okay. I will stop there. I don't actually have an end slide. I'll leave you on this one because this one may be the most interesting thing to you, which is a way to use Stan without using Stan's inference in case you want to evaluate your own.
Thank you, Bob, for the very interesting introduction of Stan. Now is a good time for question. I'll stop the recording.